nice buzzword, Internet of Things. It's everywhere. We see lots of startups. Anything you read, it's related to Internet of Things. And what this gives us rise to is another buzzword, big data, because you have these devices connected in all parts of your life. You go home, smartphones, smart fridges, smart kitchens, giving rise to a lot of data that is being collected. And with this a lot of data, we have a key question. How do we make useful inferences based on this data? Because although we are collecting a lot of data, it will be useful only if we can make something interesting inferences out of this data. So let's start with this simple example of what I mean in terms of what kind of data we can get and what kind of inferences we might be interested in. So suppose in case of smart cities, we'll of course expect that there will be an alarm system that will be in every house, which let's say not very fancy alarm system. So in this case, it either responds to burglary in the house or earthquake. It's connected to the central dispatcher. Of course, it's automated dispatcher. And suppose one of the alarm goes off. So at this point, it is very important for the dispatcher to infer whether it's because of burglary or earthquake, because since the responses to the two are different. And this will allow efficient use of resources if we can make good inferences based on the events that we got. So what we are interested here is that we want to find what is the probability of earthquake given the alarm sounded. And we have access to all this data that we have been collecting for a long time. So this is form of a general problem that is called probabilistic inference. In general, what we usually try to find is what is the probability of event of interest given some evidence. So in this case, the event of interest is earthquake, and the evidence that we have, or the observation we have, is that alarm sounded. So how do we do this? Well, we go all the way back to 1700s and go to Bayes. So the Bayes rule tells us that we can calculate probability of E given A. So E is I'm using for earthquake, A for alarm sounding. It's probability of E and A divided by probability of A. So how do we calculate these probabilities? Well, to do that first, we'll have to see how are we representing all the data that we have been collecting. So last 2 decades, there have been a lot of models proposed, and one of the very popular ones is graphical models. Since there's a name graph inside it, so we will have some nodes. In this case, we start with 3 nodes: B is for burglary, E for earthquake, A for alarm. These graphical models represent the conditional dependencies between different events, which we do by arrows. So in this case, we have an arrow between B and A, which says that A depends on B and A also depends on E. Based on data, we can also assign probabilities for the nodes. So in this case, we have a small table which is called conditional probability table if it is conditioned, or in this case, just the initial probability table. So here we say that E is true is probability with 0.1, false is probability 0.9. Similarly for B, we have that B is true with probability 0.8, certainly not a nice neighborhood to live in, and false with probability 0.2. Once we have these probabilities, we also, based on the data, we determine what is called conditional probability table. So in this case, we are interested in probability of A given E and B. So every row here says true, true, true. It says that alarm sounded given burglary and earthquake, both of them happen, and that is 0.3. The complement of that, alarm does not sound, given both of them happen, both of these should add to 1, so that is 0.7. And so on, we get different probabilities for this case, looks like we don't have a really good alarm system, and that might be the case when there are lots of faulty systems. So this is just one of the cases. You can model. It's modeled based on the systems we put in place. So once we have these probability tables, let's go back to our question. So we are going to calculate the numerator and denominator differently. So the first case is probability of E and A, which was earthquake and alarm both happening. So that we can write as sum of the two probability tables, and this is a joint distribution, so we can expand it. This going back to basic high school mathematics. This is probability of E multiplied by probability of not B given probability of A, E and not B. The other case is probability of B happening. So just expand it, simple high school mathematics. So once we have this, what do these terms mean? How do we calculate these? Well, these just become multiplying the corresponding cells. So let's see, probability of E, when we say E, it says E is true, so we will take this row. Probability of B, this 0.8, and A given EB, it becomes 0.3. So we can take, all we have to now do is to pick the right cells, we multiply them, and we multiply in the other case where E not B and A E given not B. So the error should have been here, so 0.2, 0.2 and 0.1. So we started with lot of data. One can model this data, and the inference problem, just going over the conditional probability expression we got and finding the corresponding terms in these tables, and then just multiplying the terms correctly. However, you can very soon see that this is not going to be really scalable, because the systems we have are very complicated. There are exponentially many terms here. So just trying to do the naive way is not going to work, because we'll have to find too many cells. The expressions are going to be too long. And this, of course, has been realized for a long time. There has been a lot of techniques proposed in variety from different aspects of machine learning. There are things called Monte Carlo Markov chain, MCMC based methods which try to get approximate answers, and variational methods, lots of different techniques. And all of them try to deal with doing some sort of heuristics to compute approximate values. So what I'll be doing now is to take this problem that is more the machine learning problem, and we go to logic. So let's move from probability to logic, because this problem has very nice relationship in what we study in logic. So let X be the set of variables A, B, E. All of them are Boolean variables. Let F be the formula E and A, and we define a weight function. And if you have been seeing the truth table, it is just defining the weight function based on the values we had in the probability table. So the weight function just copies the probability tables. Nothing fancy so far. We define weight of an assignment as weight of the product of its literals. Very similar to what we were doing in the probability in our graphical model. And for this formula, we denote RF as the solution space of the formula. So RF here says, if you look at this formula, this is defined over 3 variables, so it has 3 satisfying assignments. A satisfying assignment is assignment to its variables such that the formula returns true. So E and A, both of them has to be true, which we denote by 1. B can take values both 0 and 1. Now if we define the weight of formula F as the weight of sum of the weight of its satisfying assignments, then what we observe is that weight of F is essentially equal to probability of E and F. It's very simple translation. There's nothing too fancy here. If you try to see the symbols, the intersection becomes and in the logical sense, and all the definitions just follow. And this is what is known as the problem of weighted model counting. So given a formula, the problem of computing probability of E and A can be reduced to computing weighted model count of the formula. This was the reduction that I just described is not new. It is known for over almost 20 years. And the problem is, given a graphical model and the problem of probabilistic inference, you can reduce to doing a weighted model counting for the transform formulas and the weight functions. This is due to Dan Roth from UIUC in 1996. So let me first try to define more formally what is the problem of weighted model counting, and before that I'll have to define a simpler variant, which is unweighted model counting. So the problem of unweighted model counting is that given a Boolean formula F, we want to count the number of models of F. Model is a satisfying assignment, just a fancy term that logicians use. So if formula is A or B, then it has 3 satisfying assignments. Both of them can take value true, or one of them can take true, the other one with false. And now the problem of unweighted model counting is to estimate this number 3. This seemingly simple problem is actually very hard in theory. In complexity sense, this is not to be Sharpe complete. It's a canonical Sharpe complete problem, where Sharpe is a class of counting problems whose decision problems lie in NP. What it means compared to when you look at Sharpe, NP looks way too easy. So pretty hard problem. So now moving on from unweighted model counting to weighted model counting, in addition to the formula, we also have a weight function. So we had the formula and we have a weight function that is over literal. So which basically means we assign weight of A equals to 0 and A equals to 1, and they are normalized. So weight of A equals to 1 is 1 minus weight of A equals to 0. Weight of an assignment is product of weight of its literals. And the problem of weighted model counting is to sum the weight of satisfying assignments. So in our case, it becomes weight of F becomes weight of these 3 satisfying assignments, and if my calculations are right, the number we should be getting should be 29 by 32. So the unweighted model counting dealt with only finding the number of satisfying assignment. In this case, we want to estimate the weight of the sum of the weight of satisfying assignments. So you might be wondering that why are we talking about all this logic? Why did we even start from a problem that was more machine learning? We should have gone for more ML techniques. Why are we even doing this logical transformation? And the reason for this is twofold. One, counting is, the other technique we were talking about is enumeration. We were trying to enumerate all possibilities. But in complexity theory sense, it is considered easier than enumeration. The reason I have italicized is there are quite a few complexity questions which are still not resolved. We don't have to go into those details, but usually we find that counting is, in complexity sense, considered far easier than enumeration. And what we have seen is that counting techniques that are based on set. So the formulas we are talking about Boolean formulas, and there have been a lot of set solvers built on those. So there have been a lot of work on developing counting techniques for the set formulas. They have really efficient operations that can avoid enumeration. The third reason, set solvers have improved dramatically over last 1 decade. What a lot of people like to say is that NP is the new P. So N is for new because NP now becomes very simple. You had a set solver which can solve millions of variables of problems just within like under a second. So Um, to see how good the progress has been, I just grabbed a graph depicting the progress of set solvers. On x-axis, the set solvers every year are listed. So there's a set competition which tries to which is the competition among different set solvers, and it lists the winners in every year. On y-axis, the speed up in the log scale. So what we see is that over a period of 12 years, the speed up was about 1,000 times. So very similar to what Moore's law does in the world of computing. So every year, set solvers have almost been following Moore's law, and if something is following Moore's law, it's better to work with it than not to do. So in other words, more closer to where we live, we sort of treat probabilistic inference as the cowboy, and we have a good horse set solver. So what we are going to do, we are going to solve the problem of probabilistic inference using really good set solving techniques. So the motivation for this was that probabilistic inference can be reduced to weighted model counting. Weighted model counting is the problem of computing the sum of weight of satisfying assignments. And our goal is to design efficient algorithms for WMC. WMC and UMC are not new problems. There has been a lot of work since they were introduced in late 1970s. There have been a lot of work on building really good UMC solvers on a variety of techniques that we don't have to go into details, and there are a lot of solvers that are competitive and implement all of these different techniques. So that's what has happened for UMC. For WMC, the story is slightly complicated. What usually happens is there's a UMC solver. Since although the two problems look, WMC looks harder than UMC, but in complexity sense, both of them are in the same complexity class. So what people do is take the UMC solver and then they manually adapt it to a WMC solver. And that led to rise to few of the WMC solvers. However, this process has not been really working well. For example, one of the state of art, which used to be state of art's WMC counter, was not fixed for last several years. So the idea of taking a UMC solver, manually adapting is very error prone and has not been working well. Furthermore, every time there is a new UMC implementation based on new algorithms, it requires real intimate understanding of what is the UMC algorithm is doing and what will be the corresponding WMC algorithm. So in this work, our focus is to circumvent this and do something so that we can use all the progress that happens on UMC. UMC is a clean problem, so people like to work on it, and WMC is useful problem, so we want to solve the useful problem by using people's interest in clean problem. So what we do here is that we propose a transformation that takes the formula f, the weight function w, transforms into a formula f prime, and so that if you compute the UMC unweighted model count of f prime, the weighted model count of f is multiplying some constant that depends on the weight function and the unweighted model count of f prime. So what this furthermore, we propose a very efficient polynomial time reduction that reduces the problem of WMC to UMC. This allows us to use any UMC solver that can be viewed as a black box to compute UMC for a given formula. Our reduction has theoretical guarantees of near optimality, and the implementation scales to significantly larger formula than prior state-of-art WMC solvers. So let me now talk about the key idea. How do we do this reduction? So what I will be doing is to take an example and try to show you how the reduction works and then abstract away the important details. So we'll be working with the formula x1 or x2, not too hard. Very simple weight functions. since we talk about computers, so we'll be talking about the binary representation. So weight of x1 equals to 1 is 3 over 2 raised to 2 square. I know you are like, why did I just not put 4? It will become apparent later. So for now, bear with me. I'll like to call it 2 square. On the other side, weight of x2 equals to 1 is 1 by 2 square. Remember, they are normalized, so we can compute weight of x1 equals to 0 and x2 equals to 0. So I hope if you have been following me for so far, the weight of f is the sum of the weight of these 3 satisfying assignments, and when we do these calculations, it turns out 13 over 16. So now, just for some time, let's assume that f prime is this formula, x1 or x2, and x1 if and only if a1 or a2, x2 if and only if a3 and a4. So we introduce some extra variables. We are talking about a new formula. Let's look at few interesting things here, which is, I'll focus on the satisfying assignments. So I'm looking at the satisfying assignments of f prime. So x1 equals to 1, x2 equals to 1. So this is the assignment to x1 and x2, and I want to know how many extra satisfying assignments do I get for f prime. So x1 and x2 has to be 1. So that says a1 or a2 has to be 1. And in this case, a3, a4 has no choice but to be true. So we actually get 3 satisfying assignments. Because a1 or a2 has to be 1, so one of them can be 1, the other one can be 0, or both of them can be 1. So what happened here is that it had the weight 3 over 16. And we extended it to 3 satisfying assignments, right? Let's try something else. x1 equals to 0, x2 equals to 1. So x1 0 implies that a1 and a2, both of them have to be 0, right? That's the or, again, middle school math. a3, x2 1 implies a3 and a4, both of them have to be 1. We actually have one satisfying assignment. There are no other. Once you assign x1 equals to 0 and x2 equals to 1, you only have these choices for a1, a2, a3, a4. You notice it had 1 by 16 solutions, and we extended it to 1 solution, basically, just that one we have right here. If we do a bit of pattern matching, so far what we had is with weight 3 by 16 we extended to 3 solutions, with weight 1 by 16 we extended to 1 solution. For the assignment x1 equals to 1, x2 equals to 0, the weight is 9 by 16, which is because 3 by 4 into 1 by, into 3 by 4, remember this is x2 equals to 1 is 1 by 4, so x2 equals to 0 is 3 by 4, so it's 9 by 16. And we can probably trust in nature, it should extend to 9 solutions. And it does if you look at it carefully. So I guess now the last one is clear, right? x1 equals to 0 and x2 equals to 0 extends to 3 solutions. Well, not really. Oh, it should have been crossed. Because this is not a satisfying assignment. So you cannot really extend it. Since in a formula all of these clauses has to be true, so in this case x1 equals to 0, x2 equals to 0, you can't really extend it to make a satisfying assignment. Okay? If it was not purple, you would see that I crossed out 3, it's not 30. If you are wondering what kind of system I use. So let's also try to find something else. What is the unweighted model count of f prime? It It is actually 3 plus 1 plus 9. And that's number 13. Lucky or unlucky depends on your affiliation. The weighted model count of F was, if you remember, slightly long ago it was 13 over 16, right? I can write 13 over 16 this way. 2 raised to minus 2 plus 2. 2 raised to minus 4 is 1 by 16. And if I multiply it by F prime, I do get 13. So 2 raised to minus 4 into 13 is 13 over 16. So that is precisely our transform. What we do here is a satisfying assignment sigma with the weight k over 2 raised to m has to be extended to k satisfying assignments. How do we do that? We introduce these formulas x1, a1 or a2 and x2, a3 and a4. So let me try to write down in some, let's try to abstract it away. So it was f prime, f and x1 if and only if. There was something here, so that I am trying to come up with a notation for this. So my notation is that it's over 2 variables, so I use 2 here, and it has 3 satisfying assignments. Okay? So I say if and only p of 3 comma 2. By that logic, what should be in the next case? 1 comma 2. Yeah? In this work, we introduce what we call as chain formulas. The formula that can essentially, you can write as ki comma mi. It is over mi variables and it has ki satisfying assignments. So what we have in general, if the formula is over x1 to xn variables, if the weight of xi equals to 1 is ki over 2 raised to mi, then the function f, the formula f prime we construct is f and then conjuncted with all these clauses which are xi if and only if p of ki comma mi. And this does give us the guarantee that weighted model count of f is 2 raised to minus m unweighted model count of f prime, and my bad, it should have been m equals to sigma of mi. So one thing that I will not be talking about in this talk is to how to construct these formulas. We propose very efficient linear time algorithm to construct these formulas, that you can always take ki comma mi and you can always construct these formulas, and a very simple nice structure, and that structure has a structure of something like chains, at least that's what we see, so we call them as chain formulas. One thing I did not talk about, which is usually important, is conjunctive normal form. When you talk about set or Boolean formulas, you ask, how do I represent this? Well, you can always write just in the way you want. You can put your operators wherever you want. But over last few years, people have agreed to represent them in one form because this allows to build really good set solvers, since this form has a lot of interesting properties. And this is called conjunctive normal form. So what we have is that we have clauses and they are connected by the operator AND. And in every clause we will have the OR operators. Okay? And in this case the clauses have 3 variables, and if you have been following these questions like P and P, so they usually talk about the formula that are called 3 set. So what we got here is f prime, f and omega. If I denote the big expression that we were getting, xi if and only if p of ki comma mi by omega, then the transform formula that we get is f prime equals to f and omega. It is very important to preserve the CNF form because that's what is required for most of the set solvers, and they can only use the CNF form as the input. And what we show is that this formula that we get omega, it can be expressed in CNF in polynomial time and with only in a very small size, which is sigma of mi square. Furthermore, if f is in CNF, then we can also have f prime can be. This gives rise to the theorem that since f is already in CNF, omega we can convert in CNF in polynomial time, and when you take conjunction of two CNF formulas, you still get a CNF formula. So the resulting formula that we get is a CNF with very low overhead, and we can give this to a UMC solver. I think you might be wondering that, wow, the reduction seems very simple, so is it even optimal? Well, it turns out what we show is that if you take if there is any algorithm that exists and which returns a formula f prime of such that weight of f will be of this form, where Rf prime is the UMC of f prime. In our case, dw was 0, but even if you can allow it to add some constant, then what we say is that what we showed is that the f prime has to have n plus capital M minus k variables, where k is a function of w weight function. I did not put it since it was making the slides ugly. In this case, our transformation results in the formula f hat with n plus m variables. So we are off by a small additive factor of k. So that's for the theory. We started with,
just to clarify, well, how is k related to ki of that? Is k the sum of the ki's?
oh, that's my bad notice. No, it's completely,
It's different.
yeah, it's different. I mean, it depends on the weight function, but nothing directly different. I should have used some other notice. Thank you. So how will we do in practice? Because all of this was motivated that we wanted to design really good weighted model counting solvers, right? So just to recap, we had this transformation which reduces to formula f prime, and then we want to use a UMC tool at the back end. In this case, we use two state-of-art UMC tools which are called sharp set and D sharp. If you are wondering why there is sharp name here, because this problem it's the sharply complete, so people are not too creative, so they try to put sharp here and there. And our transformation, of course, gives the property that once we know the unweighted model count, the CW is very simple. It's just 2 raised to minus n, right? So even humans can do it. You don't even require someone to do multiplication. So we wanted to see how well we do. To do that, we took benchmarks that come from variety of applications, grid networks, sizing models, planning, program synthesis, which is emerging as an interesting area in last few years. We compare it to the, of course, the state-of-art weighted model counter, which is SDD, developed from UCLA. And as I said, the UMC solvers that we use are sharp set, D sharp at the back end. We can use anything you give. So one of our collaborators likes to call it frog. So you can use any solver that you give on the back end. How well we do? So there should have been the name of benchmarks, but I could not figure out how to force PowerPoint 2016 to put those benchmarks. On y-axis, I am presenting the time in log scale. Okay. On x-axis, a lot of benchmarks. And the time what we used was 18,000 seconds. And what we see is that actually SDD times out on almost all the benchmarks. And even on the ones where it does not time out, we are usually 1 to 2 orders of magnitude faster than SDD. And SDD was the state-of-art WMC solver before this transformation. Alright, so to conclude, the problem of weighted model counting is interesting because probabilistic inference can be reduced to it. Over the last few years, there has been a lot of work on developing good WMC solvers. Prior work required taking a UMC solver, making someone sit, usually a graduate student for a few years, and building a WMC solver. In this case, we give a polynomial time transformation from WMC to UMC. As I promised, all the stuff we did was most of the times except for a few theorems, high school math. And the resulting tool, weight count, outperforms state-of-art counters such as SDD by 1 to 2 orders of magnitude. With that, I'll be happy to take any questions. Thank you for listening.
So, for experiments you're doing, approximately how big is M? Because if you have really good probabilities, then your M is small. Like if you have something over 4, something over 8, then M is small, then you get a smaller formula, whereas if it's lasting to 16 bits, then it's going to be a lot.
So, these benchmarks where we took in every conditional probability, so we can talk about MI because that's what sort of makes sense. M is usually pretty large, but every MI that we have was up to 2 precision, so which becomes, MI becomes like 1 by 2 raised to 128, so 7. So every MI, and these formulas have like, tens of thousands of variables, so that makes M to be 70,000, 50,000, pretty large. Yeah.
In the 5 formulas that you appended to F, were K and M the parameters you use to generate phi, or?
Yeah.
But I mean, if I understand correctly, M is the sum of all MIs, right? So then that should have been
It was KI MI.
right, but the MIs were summing to M, which is what you wanted to find out in the first place.
Yeah.
So how can that be an input to your formula?
No, we were not finding M. We exactly know the M because every representation we know is power of 2, 2 squared, so we know the M. What we are trying to find is the unweighted model count of F prime. So 2 raised to minus M, you just know it. You look at the formula and you say, alright, I can count. Because if we have some time, and if no one asks questions, you'll have to listen to one more slide to show how to construct this formula. Yeah, okay.
So probabilities are always p to the power 2 by 2 power m. How do these extend to general probabilities like p by q?
Well, two things. One, in this reduction, we can actually handle general case, which I did not talk about. But the other thing, if you are giving it to a machine, it has to be a binary representation, whatever you give.
But if it's a binary representation, can be something like summation 2 power mi, where mi does not. It
No,
can be
that's-
summation 2 power mi, right? It doesn't
Yeah,
have to be 2
no.
power.
Then you will actually still get some power of 2.
So are you approximating the probabilities?
No, if you are giving it a machine representation, then it is sigma of ki over 2 raised to mi. You do all of this, the denominator is capital 2 raised to mi, and then the numerator. It still will. It's a binary representation, so this is what you will get. You can take it offline. It's just like the decimals. You can divide everything by 10 power of 10. If someone gets 0.13, it is 13 by 10 raised to 10 square. This is Boolean word, so it is k over 2 raised to 1.
Can you spend some time describing this one?
Yeah, this looks exciting, right? Alright, so, and, okay. So, actually it turns out that this reduction, after a few iterations we went through, finally the algorithm is really simple. So how do we construct such? On this side I'll be presenting the steps of algorithm, on the other side the examples. So let's say we want to construct P of ki comma mi. So what we have, it should be mi. So we write, we had to introduce new variables, so we write a1, a2 to ami. Okay? And in all of those we leave one space. right? This is going to be really tricky. You take ki, you have a binary representation of this in mi bits. Wow. Let's say ki is 5, mi is 3. So you had 3 variables, a1 space, a2 space, a3. And these brackets, right? That's more like medicine. Yeah, so keep watching here. We want ki 5. How do we represent ki in binary? 1, 0, 1. Right? 1 plus 2 raised to 2. We throw away the last one. So we have 1, 0. We put these 1, 0 just like that way. Just drop them out of the spaces. So it is a1, 1, a2, 0. And you replace 1 by or, 0 by n. That does work. Now there is a proof that we will have to take offline. The beauty is in the simple reduction. So as I promised, all of this is high school, except for the police.
Any other questions?
I can take it.
All right. Well, thank you.
Okay.
We've got 2 small trash cans today. Please take your water bottles out to the recycling bins, please, so that they don't fill up the little trash cans. And remember to go to Owlspace to do your feedback survey.
And the examples, they are actually, we calculate 2.